exposed. Just think of COVID-19. The pandemic is going on. We are all susceptible. You got exposed. After that, you're going to have a subclinical disease wherein you're not yet symptomatic, wherein pathological changes are ongoing. Finally, you have symptoms. You have fever. You start coughing, and after that, you feel that okay, I need to get tested. So you get a test done, and this is the usual time of diagnosis. So you are in a clinical disease. After that, hopefully you recover or disability or death happens. So this is how a natural course of any disease happens. What they ask you is they label these points A, B, C, and D, and they'll ask you to identify these points. So first is exposure, second is subclinical or pathological changes, C is symptomatic, D is diagnosis. Now, what is the lead? So lead time is when you make a diagnosis by screening. When you do a screening test, you do a screening test in asymptomatic population, isn't it? And the aim of screening is to pick up a disease earlier. Usual time of diagnosis when you pick up a disease at point B, when the patient is not yet symptomatic, when the patient is in subclinical disease, before onset of symptoms, that is the purpose of screening, early diagnosis. So this is what is called as the lead time, is the time that you have increased from D to B. All right, so from D to B, when you pick up the disease earlier, that is called as lead time, and that is also one bias. All right, so that is what is called as a lead time bias. When you pick up the disease earlier, the patient feels I've been diseased longer. This apparent increase in the duration of disease because of picking it up earlier is known as a lead time bias. So you just want to remember what is lead time or lead point. It is this D to B. This is a repeat right? I hope you got the concept that we're picking up the disease earlier at point B by screen. All right, so screening basically helps from B to B. Okay, now let's talk about very, very important levels of prevention. This is where you usually get at least one question from. So there are 4 levels of prevention: primordial, primary, secondary, tertiary. Here what they're going to do is they're going to give you examples and will ask you what is the level of prevention. So just understand the concept and you'll never get this wrong. So primordial. Prevention is when there are no risk factors and there is obviously no disease. So when you do not even allow the risk factors to come in, this is achieved through health education. For example, if somebody who's never smoked, who's never had alcohol, who's adopted a very traditional conservative lifestyle, you are avoiding all risk factors. So adopting this traditional lifestyle without any risk factors is what is primordial level of prevention. This is something very rare. The most common that you're going to have, and logically, if you are stuck in the exam, you don't know what is the answer, you mark primary. Or like just take it from me. If you don't know the answer, you mark primary level of prevention. Primary level of prevention means that the risk factors are there. The disease has not yet developed. So this can be achieved by 2 things. One is health promotion. You change your lifestyle. A person who was a drinker, a smoker, is cutting down. So you're reducing smoking, or you're giving up smoking. You're reducing alcohol. You're giving up alcohol, and now changing your lifestyle for the better. That is a primary level of prevention. Means you are reducing your chances of developing the disease, but risk factors are already there. So this is a general overall health promotion, being a healthier person. Specific protection are, the examples which get tested in the exam. So something like a vaccination. Most frequently asked. Vaccination, any sort of vaccine, which you take as a child or you take after exposure, even post-exposure prophylaxis. This is where students mess it up. All right. So post-exposure prophylaxis also, risk factor is there, but you're not yet diseased. So all of these become specific protection. All right. I hope this is clear. We'll be looking at more examples. Secondary level of prevention is what happens after you have the disease. All right. So risk factor to chodo, now you have the disease. All right. So then secondary level of prevention is you pick it up earlier, and the biggest example is screening. So when I said that if you don't know, you mark primary, the only exception is remember, sir for screening, sir for secondary. All right. This is what is the most important. That by screening you are diagnosing things earlier. This is not a primary level prevention. This is a secondary level of prevention. And obviously when you treat, that's a secondary level. You're already diseased, you are treating. Okay. Tertiary level of prevention is not just disease. You also now have the effects of the disease in the form of some sort of disability, and that you are trying to correct in the form of disability limitation or rehabilitation. Meaning, if you had polio and now you are using crutches or you're using some sort of aids, that is a tertiary kind of prevention. When you're doing physiotherapy, that is a tertiary kind of prevention because now you have the disability as well. When you're using contact lenses, you have the disability because of refractory errors and you are correcting that. So that's also tertiary level of prevention. Okay. So I hope this is clear. The concept is clear. Disability because of refractory errors and you are correcting that. So that's also tertiary level of prevention. Okay. So I hope this is clear. The concept is clear. All possible questions I've tried to include in this list. So now let's test ourselves. What are vaccines? Vaccines are when risk factor is there, disease is not there. So this is primary level, specific protection. What about post-exposure prophylaxis? Again, same. Primary level of prevention, specific protection. But when you're using BCG for CA, UV, carcinoma, UV treatment, isn't it? So this is secondary. What about contraceptives? Again, contraceptives here consider pregnancy to be a disease. Risk factor is there, but disease. You don't want pregnancy. So you're using contraception becomes primary, specific protection. OCT is used for PCOD. So OCT technically is a contraceptive, but when you use it for PCOD, you're using it for treatment. So this is secondary. What is screening? I told you S for secondary. Alright, so this is secondary. Physiotherapy for polio, tertiary. So the gist, the summary out of this is when you don't know, you mark primary specific protection, except screening, diagnosis and rehabilitation, you will pick up only this. You will not ever be confused with. Alright. Okay. Then when you're giving chemo prophylaxis in alright, so this is secondary. Physiotherapy for polio, tertiary. So the gist, the summary out of this is when you don't know, you mark primary specific protection, except screening, diagnosis and rehabilitation, you will pick up only this. You will not ever be confused with. Alright. Okay. Then when you're giving chemo prophylaxis in contacts, meaning you have been exposed but disease has still not come. So again, what did I tell you? Primary specific protection. Using mosquito repellents, nets, PGD. Risk factor is there, disease is not there. Primary specific protection. Using iron folate, you don't want the disease to come. So primary specific protection. Seatbelt helmet, you don't want to die. Primary specific protection. Risk factor is there. Fetal ultrasound. What is fetal ultrasound? So you are trying to pick up anomalies earlier, isn't it? So you are trying to pick up the anomalies earlier. So this is when you are. So this is when you are trying to make an early diagnosis. This is sort of a screening, isn't it? Fetal ultrasound anomaly scan is a screening test. So this is secondary. All right. So just use logic and everything will make sense. So now let's look at a few important definitions. These are very very important, and you get a lot of questions from these, and these are very confusing. So you have to put this in your choti copy and revise this. Believe me, you will confuse them. Okay. So the first thing is, what do you call the first case to occur in the community. This is the primary case. All right, so you remember primary case is the first one to occur and the first observed case is the index case. So the first case who comes to the epidemiologist or the clinician is the index case. So I and O, vowels stick together, and you remember CP. All right, CP is also something we've done a lot of times, like Coles is posterior, and you remember staging of cervical, endometrial CA, we've done CPR. So this is CP and vowel sticking together. Then 3 time intervals. What is the time between a primary and a secondary case? First and a second person to be infected. This is the serial interval. All right, so serial interval between 2 people. Time between entry of organism and the symptoms to occur is the incubation period. Very basic, I'm sure you know this. Incubation period when it becomes symptomatic. Time between entry of organism and maximum communicability. Very, very important is the generation. I'm sure you know this. Incubation period when serial interval between 2 people. Time between entry of organism and the symptoms to occur is the incubation period. Very basic, I'm sure you know this. Incubation period when it becomes symptomatic. Time between entry of organism and maximum communicability. Very, very important is the generation time. This is, in my opinion, the highest chance of getting asked. Entry of organism, maximum communicability. Okay. Now, difference between isolation and quarantine. So, isolation is of a diseased person, whereas quarantine is for a healthy person. So, let's say that you have a case of measles. You isolate that case to protect the others from getting infected. Quarantine is of a healthy person who has not yet developed symptoms but has been exposed. And sure, you all know quarantine from the COVID pandemic that we all faced, isn't it? So, therein, any person who's had international travel has to be quarantined for that period where he can transmit that infection. So, diseased and healthy, very, very important. Isolation, quarantine. Quarantine period of yellow fever has been asked specifically. So, just remember this one number, it is 6 days. Then we talk about 2 definitions of health indicators. First is virulence of disease. Virulence of disease is indicated by CFR, that is case fatality rate. Is a misnomer, it is actually a proportion. So, case fatality rate is number of deaths upon total population into 100. So, anytime the denominator includes the numerator, it is called a proportion. All right. So, remember, case fatality rate is actually a proportion because it is the number of deaths upon the total number of infections or the infected population that you have into 100. All right. And communicability of the disease is indicated by SAR, secondary attack rate. I'm sure you have heard this all over the place in the COVID pandemic. So this is secondary attack rate, which indicates the communicability of a disease. Now we move on to the most important part, which is epidemiology. All right. So we are going to be first starting off with the studies. So there are 3 types of epidemiological studies that you have. The broad classification that you first want to understand, again, here We are going to go into a very baby stepwise approach, and this is what you will follow in order to understand. So the first broad classification of the studies would be whether they are descriptive, analytical, or experimental. In order to study anything, we need a hypothesis. Descriptive studies when you formulate a hypothesis that there seems to be a connection between smoking and CLR. That is descriptive. When you test the hypothesis, that is there really is there really a connection between smoking and CA lung? Let me take a bunch of patients of CA lung and study. So whenever you are testing, that is analytical. Experimental is when you confirm that hypothesis. All right, you do a randomized control trial and you confirm. So this is the broad category: formulate, test, confirm. Right now, descriptive and analytical are both non-experimental or observational studies. So one way is observational versus non-observational. Observational or non-experimental versus experimental. All right, so this is your first category. I hope you understood. Within observation, we have to see what is the unit of study. Usually, the unit of study is one individual, but when the unit of study is population, very important, population-based analytical study. What comes under this? It is ecological study. Ecological study is also called as a correlation study or an aggregation study. Very important. This is what takes secondary data. All of these numbers are very important. And one thing that you want to remember here is there is something known as ecological fallacy. So what is this? So in ecological studies, what we are doing is that I'm studying the population of the different countries of the world, and I'm saying that per capita meat consumption of India is this much, of Australia is this. The study is also called as a correlation study or an aggregation study. Very important. This is what takes secondary data. All of these numbers are very, very important. And one thing that you want to remember here is that now connected to iPad policy. So what is this? So in ecological studies, what we are doing is that I'm studying the population of the different countries of the world, and I'm saying that per capita meat consumption of India is this much, of Australia is this much, of US is this much. But the policy here, the ecological policy is there. Me as a person is not being represented. Let's say I am studying per capita meat consumption, and I'm saying that for Indians, this is what is the amount. But then there is the strict vegetarian who's sitting there and wondering, I'm not even eating this much meat. How did this come into picture? So basically, we cannot generalize it for each and every individual. It is for the population in general. That is the ecological policy. Okay, and that is why we are using secondary data here for the population. Okay, so this is what you want to know, where the unit is of population. Very important. Then when you go to individuals as a unit, in descriptive studies, what are included are case reports, case series. Once you get into your residency, you're going to be writing a whole lot of these. So these are when you describe that I saw an interesting case who had these kind of findings. All right, when you describe a bunch of cases of similar findings, that's called a case series. Okay. Then we have analytical studies. So in analytical studies, three most important. This is what you get bulk of questions from: cross-sectional studies. Okay. Then we have analytical studies. So in analytical studies, three most important. This is what you get bulk of questions from: cross-sectional study or a prevalence study. This is a snapshot, meaning this is taken at one time point. So you go to the community right now, gather the information of all of that population, you see what is the prevalence of CA lung, all right, at that particular point of time. So prevalence is at one point of time. What is the proportion of cases? That is prevalence study. Remember, this is what gathers primary data. All right, so this is cross-sectional one-time point. Case control cohort are your linear studies. So case control is also called as case reference, and cohort is also called as a follow-up study. We will talk about these in general because this is the most important. Finally, going on to experimental, you have randomized and you have non-randomized studies. In randomized control trials, you have clinical trials, you have crossover trials. Crossover trials meaning, let's say you are testing a drug. So you divide your study population into those who are getting that drug and into those who are getting a placebo. All right. So this is your division. After a washout period, you will cross these patients. The patients who were receiving the drug, then they get placebo, and the other patients will get the drug. So this is called as a crossover trial, and this period in between is called as the washout period of the drug that was being given. All right. So this is crossover, which is a subdivision of clinical trial. Non-randomized trial would be field trial, community trial, which are usually done for vaccines, and these are there.
These are useful for public health intervention assessment, sometimes also known as community trials.
Healthy population are also included. Okay, so this is about the broad division. Very, very important slide. Okay, now something that is most important is case control versus cohort. So first, let's try and understand.
case linear control.
Basis of these images. If you do this slide, all of the questions get sorted. Okay. So this is where we come in. We are the examiner. So I take diseased and non-diseased. I take cases and I take controls. Controls are those who don't have the disease, and I go back in time and find out if they have been exposed to the risk factor or not. So I take CA lung patients and I take normal patients, and I ask them both whether smoking history is there or not. So when you go from the disease to the exposure, this is what is called as a case control. Just remember that smoking history is there or not. So when you go from the disease to the exposure, this is what is called as a case control. Just remember the name and it becomes easy. You are taking cases, you are taking controls, you are taking disease, you are taking non-disease. Okay? But when you start from exposure, this is when you are starting from exposure to disease. You take a cohort population. You take a population who have exposure, who have non-exposure, who are smokers, who are non-smokers, and you observe them over 10 years to see if they develop CA lung or not. So you come in between, you see if disease comes or not. So you're going from exposure to disease. This is what is called as cohort, which is prospective cohort. All right. So this is your prospective cohort. You are going in time. Okay, but as you can understand, this is something that is very time consuming. It is going to take up a lot of years of your life. So what else you can do is retrospective cohort. It goes in the same order when you are starting from exposure and you are going to disease. So just because the name is cohort, it has to be exposure to disease. But then you are collecting this data afterwards. So you are not going with time later on. Right now, if I take up a bunch of smokers and non-smokers from their historical records, hospital records, and then I see if they develop CA lung or not, this is what we call as a cohort, which is retrospective cohort. Alright, so this is retrospective cohort when you are taking the data from the records, but it is exposure to disease. Alright, so I hope you understood the difference. So this is what you actually focus on, whether it's disease to exposure you're going or you're going from exposure to disease. Another confusing thing here is a nested. If I take up a bunch of smokers and non-smokers from their historical records, hospital records, and then I see if they develop CA lung or not, this is what we call as a cohort, which is retrospective cohort. All right, so this is retrospective cohort when you are taking the data data from the records, but it is exposure to disease. All right, so I hope you understood the difference. So this is what you actually focus on, whether it's disease to exposure you're going or you're going from exposure to disease. Another confusing thing here is a nested case control study. So in a nested case control study, what you are doing is it's traditionally a cohort within which there is a case control. So this is done when you have a very, very rare disease or a rare investigation that you are trying to see. So let's say that there are a bunch of newborns in the hospital. We are taking all of the records of that cohort. All right, so it is like a traditional cohort. So I am taking a bunch of newborns, a bunch of thousand or a 10,000 newborns. I'm taking, and I'm taking all of their historical records. I'm taking the blood sample or their stem cells or their umbilical cord sample, and I observe them for a lot of years. We see that they develop a rare disease. Let's take an example of BES-induced hypoplastic uterus or a T-shaped uterus. So let's say they develop a very rare disease. I go back in time. The population which develops that disease, we will call them as cases. And from that same population only, people who have not developed a disease, I take a subgroup and call them controls. Now I go back in time and take those history of their mothers. Were they exposed to any specific drug? So it's actually going from the disease to the exposure, right? So within this cohort, I have nested a specific case control, isn't it? So we are actually going from disease and then we are going back in time and seeing what happened. So within a cohort, we have developed or nested a case control. I hope this is clear because this is one of the most confusing aspects of epidemiological studies that there is. So you just understand disease to exposure or exposure to disease here. Okay, so these are four things, and if nothing works out, what you remember in nested is when they talk about umbilical cord, stem cell, what they're talking about is nested case control. Fine. So now let's take into account various one-liner questions that you get from these studies. When they tell you what is the best for multiple exposures, so you have a patient of CA lung and you want to test what all was he exposed to multiple exposures. So obviously answer becomes case control. But when you want to test multiple outcomes, this is a smoker. What all did he develop? We see over time. So this is cohort, isn't it? So just use logic here. Don't memorize these, use logic. Best for rare diseases. So for rare diseases, we can't do a cohort, right? It would be too time and expense intensive. So this becomes case control. Whereas for rare or expect So investigation, remember, are nested case control, isn't it? Stem cell umbilical cord. This is nested case control. What is known as incidence study? So incidence is something that is new cases which occur over a period of time. So this is only given by cohort. Remember, incidence is only given by cohort because we are establishing temporality. We are establishing new cases. Okay. Whereas prevalence or snapshot study, as we already saw, was the cross-sectional study that gives us the prevalence. Unit of study in ecological study is the population. And where does intention to treat come in? This is in randomized control trial. All right. So just remember ITT trials are RCT trials. Where does recall bias come in? So recall bias comes in case control, isn't it? So case control will have recall bias, meaning if you develop CA lung, you're more likely to remember every single cigarette that you smoked. But then if you didn't develop lung CA, that occasional cigarette smoking will not matter. So why forget about it? So that is recall bias. Selection bias again comes in case control. When you're selecting the controls, there can be selection bias. Bergsonian bias meaning in hospital. If you take your population from the hospital, that is called as Bergsonian bias because the patients who are coming to hospital are not the same as the overall community. They have a set of their own inherent factors which are not something that you can generalize. So that bias which comes in when you study population is from the hospital is called as Bergsonian bias. Alright, so these are all biases which come in from case control. Attrition bias is when you are doing a cohort study over a period they have a set of their own inherent factors, which are not something that you can generalize. So that bias which comes in when you coming to hospital are not the same as the overall community. They have a set of their own inherent factors, which are not something that you can generalize. So that bias which comes in when you study populations from the hospital only is called as Burkensonian bias. All right. So these are all biases which coming from case control. Attrition bias is when you are doing a cohort study over a period of time, some people will move to other places, will drop out. That is attrition. And Hawthorne bias is what is very important, attention bias. If these patients of cohort study know that they are being observed, they're gonna change their behavior. That this person is seeing me because I'm smoking, meaning I'm gonna develop something. Let me drop smoking. Let me change my behavior. So that is what is known as attention bias. Both of these coming in cohort studies. All right. So these are biases which are very, very important as well. So very high slide for all epidemiological studies. Now let's do the formulae. So where do you get odds ratio? Remember, you get this in a case control. Because you don't get incidence, we get odds ratio in a case control. So have you
देख जो कोहॉर्ट होता है ना उसके अंदर बहुत सारी चीजें आएंगी। कोहॉर्ट रिलेटिव रिस्क, एट्रिब्यूट रिस्क, पॉपुलेशन एट्रिब्यूट रिस्क और जो केस कंट्रोल।
Measure odds ratio, you have to draw a table. Anytime you draw a table, always keep disease as top. All right. So because when you draw these tables, the most likely error that I've seen students make is they flip the axis here. All right. So you want to remember that D always come on top. How to remember is you must have elder sisters DD. So remember DD always is upper and it's always superior. So that's how you can remember that D always comes on top. And then here we will have the risk factor in this case. Same fun time taking screening 2 by 2 table also. So there also disease comes on top and test comes on the side. Because we're talking about studies, risk factor comes on the side. All right. So this is how in the plot you will be given a whole statement and you will draw 2 by 2 table of the degree exam. Okay. So disease is there or not, risk factor is there or not, we will limit A, B, C, and D. Odds ratio is the cross product. So it is the cross product. So odds ratio would be A into D upon B into C. So AB into BC. So no shortcuts here. Just draw the 2 by 2 table, disease on top, risk factor on the side. Divide the population ABCD, ABBC is. So this is odds ratio. When we go to cohort studies, the measure that we get is the RR or the relative risk. Very important. Relative risk is the incidence in exposed upon incidence in non-exposed. Meaning, if the RR is 5, smokers are more likely to get CA lung by 5 times. Incidence in exposed upon incidence in non-exposed. So 5 times higher likelihood of CA lung developing in smokers. So this is the likelihood incidence in meaning if the RR is 5, smokers are more likely to get CA lung by 5 times. Incidence in exposed on incidence in non-exposed. So 5 times higher likelihood of CA lung developing in smokers. So this is the likelihood of developing the disease if you have that risk factor. Any RR which is more than means that there is higher risk of getting the disease. Any RR which is less than 1 meaning it is likely to be protective. The risk reduces. But any RR which is not is there is no association. There is no association between these. All right. So causative association, protective association, no association. That is the meaning of RR. Now, when I say causative, remember we can't just establish causality with one pattern. you have the whole Hills criteria for causality, and the most important Hills criteria for causality is temporality, meaning you have to establish time that this is when smoking came in and this is when CA came. So temporality is the most important criteria for causation. This is a repeat. Okay, so this is about attributable risk. So attributable risk is incidence in exposed upon incidence in non-exposed upon incidence in exposed. So what this translates to, let's say we get an attributable risk of 35%. It means that 35% of CA lung cases can be attributed to smoking. Proportion of cases which can be attributed to the risk factor is what is known as attributable risk, and population attributable risk, the formula is incidence in the total population minus incidence in non-exposed upon incidence in total. All right. So what do you want to remember? is that NE is what you are subtracting. Play from iPad. All right, and both of these, because it's a percentage, obviously you multiply with 100. So population attributable risk, let's say, comes out to be 20%. What does that mean? That if you remove the risk factor from the community entirely, if I remove smoking from the world, how many percentage of CL lung will be reduced? It is 20%. So when you remove that risk factor from the community, how much percentage of cases can be reduced is PR. All right, so two definitions very important. This is about how many cases can be attributable to the risk factor or are because of the risk factor, or PR means how many percentage cases will go down if you remove that risk factor. All right, so this is what you want to understand and remember here. So now we talk about something very important, which is known as confounding. What is a confounder? Is a factor which affects the exposure as well as outcome. So let's say we are studying the association of smoking and CLR. That's what we've been doing. But there's an independent factor which is coffee. So people who are drinking coffee are also more likely to be smokers, and we talk about something very important which is known as confounding. What is a confounder? Is a factor which affects the exposure as well as outcome. So let's say we are studying the association of some cases can be reduced is PR. All right, so two different reduced it is 20%. So when you remove that risk factor from the community, how much percentage of cases can be reduced is PR. All right, so two definitions very important. This is about how many cases can be attributable to the risk factor or are because of the risk factor, or PAR means how many percentage cases will go down if you remove that risk factor. All right, so this is what you want to understand and remember here. So now we talk about something very important which is known as confounding. What is a confounder? Is a factor which affects the exposure as well as outcome. So let's say we are studying the association of smoking and CLR. That's what we've been doing. But there's an independent factor which is coffee. So people who are drinking coffee are also more likely to be smokers, and coffee is also increasing the risk of CLR. So there is a factor which is affecting the exposure as well as outcome, and this is what we call as a confounder. Very, very important. And this is not to be confused with another factor which comes in between the exposure and outcome, which is called as an effect modifier. So in the same example, when we are studying smoking and CLR, asbestos becomes a effect modifier because patients who are minors which are exposed to asbestos and are smoking will have a higher chance of developing CLR. So this modifies the effect of smoking further. All right. So this is the difference between confounding and effect modifier. For example, what you remember is when they stress on the fact that it's related to exposure and outcome, it's a confounder. All right, and that's what usually tested. How do we eliminate confounder? So when you on the fact that it's related to exposure and outcome, it's a confounder. All right, and that's what usually tested. How do we eliminate confounder? So when you already know that coffee is a confounder, let's say you are doing a case control study, you eliminate the patients who are drinking coffee. So you are doing what you do is something known as matching. So in matching, what you do is you take equal number of coffee drinkers in cases and controls. So you will match your case and control group such that the effect is negative. Either all of them are coffee drinkers or none of them are coffee drinkers. So you match your cases and controls accordingly. So this is called known confounder. Only when you know that this is something which will affect, you can control it, isn't it? So this is matching. But to eliminate known as well as unknown confounders, we have all of these ways, which is a repeat question. So you can do randomization, you can do restriction, stratification, stratified randomization, or a multivariate analysis. They have asked this repeat question overall, which is the best. So obviously, when you can do two things, that would be better, right? So the best is stratified random. randomization. That means you stratify also, you randomize also. So stratify. Randomization. So this is for confounders. What about biases? What about all of the biases which are systematic errors? How do you eliminate that? So do not confuse all of these values. Randomization is not for bias. For bias, what we do is blinding. All right. So we do blinding B for B. For biases, which is the best kind of blinding? So you have single blinding, double blinding, and triple blinding. Single blinding is when the patient doesn't know in which group he is in. Is he in the drug group or the placebo group? To give you an example. Double blinding is when the patient and the researcher, both of them are unaware of where the patient is. All right. So neither does the patient know whether he's in control or placebo, neither I know as a doctor where he is in, so that I can be biased with my results. So this is double blinding. And what is obviously the best is the triple blinding is when neither the patient, the doctor who's treating, or the researcher who is basically governing or calculating the responses is aware. All right. So here in double blinding, it's patient or doctor basically or the researcher, and here it's all three of them who are blinded. So this triple blinding is the best, all right, to eliminate bias. Now we talk about clinical trials. This is very, very important. This comes in pharma also, so we're going to cover it right here. All of the topics from clinical trials, we got a lot of questions, all right. So now there are four phases to a clinical trial. Let's say we have developed a new drug in our lab and now you want to put it into the market. You can't straight away put it into the market. There are four phases at least which you have to undergo. So the first phase, you need to know the better improvement over existing drug? Is it better than the existing drug or not? So here we compare it with the current standard of care. So after phase three, this is where the drug can be launched. Once you've proven safety, whether it works or not, which is efficacy, and whether it's an improvement. So after this, you can launch it, and the license which you get here is a NDA, which is a new drug application. This is where you will file NDA and you will get the license. All right. So this is where NDA comes in and then you launch it. And post-market launch is the post-market launch to know whether it can stay or not. So here you want to remember N for market. So the trick is to remember SWIM. The mnemonic is SWIM, safe, work, improvement, post-market surveillance to detect any rare or long-term adverse effects, which you did not understand during the purpose of your study, but later on they are discovered after patients who for 10 years, for 15 years, then you come to know that all right, this is something which you did not anticipate. That is the phase four, so it continues forever, and these are called as black box warnings. In addition, you also want to remember that there's an optional phase, which is phase zero, which is known as the microdosing phase, and very, very expensive drugs. If there is something that you're trying to launch, before you set in a very expensive clinical trial, you can do phase zero to see whether it will work or not. All right. So this is the microdosing phase that you do for a very small number of healthy volunteers. So the study group here is healthy volunteers. This is phase zero. It is not mandatory. Okay. So these are the four phases of a clinical trial. Now we go on to very, very important chapter of screening. Again, screening, you will always have to draw a 2 by 2 table, and that is where it all starts. So as I already told you, DB comes in first. So this is disease, which is plus or minus, and what does your test say, whether it is coming positive or negative. So any person who is diseased with the test coming positive is a true positive. Let's call this A. Any person who is not diseased but the test comes out to be positive is a false positive. It is not truly positive, false positive. Let's call this B. Any Somebody who has the disease but test comes out to be negative is a false negative. Let's see. Somebody who is not diseased, test is also negative, is a true negative. D. So I hope this is clear, the definitions. What is sensitivity? So here we have sensitivity which comes into D. So this is sensitivity. So you want to remember that sensitivity is A divided by A. plus C. Vertically we are going. Okay. So this is anybody who is true positive upon TP plus false negative. All right. So how many did your test detect out of the total positives? Right. Out of the total positives, how many did your test detect? So can I also say that sensitivity is inversely proportional to false negative because it is Fn? So you remember this very important point. It will help us as we go ahead. All right. So you remember Fn and N of sensitivity. That sensitivity is inversely proportional to false negativity. All right. Then we have specificity. So same way, this is specificity. So this becomes true negative upon the total negative. So D divided by D plus B is the formula for specificity. And what can I say from here? That it is inversely proportional to B. So it is in specificity is inversely proportional to false positive. So P and P, N and N is what we remember here. Then we have positive predictive value. So positive predictive value is now going to be horizontal. So this is A divided by A plus B. Always your truths come on the top. Alright. So A and B always come on the top. So positive predictive value is out of the total population wherein the test is positive, who are really your true positive. Alright. So that is your positive predictive value. What is negative predictive value? Is out of those who have tested negative, who are truly negative. So that is
Alexa,
D divided by D.
volume 10.
And negative predictive value. One definition is prevalence. So prevalence is obviously the ones who have the disease. So that will be A plus C upon
Alexa,
the total population.
volume 9.
Okay, so this table we have to master, and I'm sure this is how we can. A plus C, this is positive and negative predictive value. One definition is prevalence. So prevalence is obviously the ones who have the disease. So that will be A plus C upon the total population, A plus B plus C plus D. Okay, so this table we have to master, and I'm sure this is how we can remember vertical, vertical, horizontal, horizontal is how you remember these formula. Nothing to memorize. Just understand. So now coming on to the most important one line. You get a lot of questions and become very confusing. So just revise this one more time. Okay. So the ability of a test to correctly identify those who have the disease is the sensitivity. All right. So this is the sensitivity. There's the ability of a test to correctly identify those without the disease. That is the true negatives becomes specificity. The true positive rate is sensitivity, whereas true negative rate is specificity is the other way of putting this. Probability that a person who has a positive test actually has the disease. So this is positive predictive value. This is the definition of PPV. Remember now that the pre-test probability is defined as the prevalence, all right, and the post-test so this is positive predictive value. This is the definition of PPV. Remember now that the pre-test probability is defined as the prevalence, all right, and the post-test probability is the PPV. So there is a very important correlation, as we mentioned, between PPV and prevalence. So pre-test probability is what is the prevalence of the disease, whereas post-test probability is the positive predictive value. Both of them are related, and we can have a Bayes theorem, which is an equation that relates the two of them. The diagnostic power of a screening test is also given by positive predictive value. This is very, very important. So remember, the most useful test for a screening test is obviously the sensitivity. That's the most useful value. But the diagnostic power is given by positive predictive value. The probability that a person with a negative test actually doesn't have the disease, so this is very full value and by positive. So them are related. So pre-test probability is what is the prevalence of the disease, whereas post-test probability is the positive predictive value. Both of them are related, and we can have a Bayes theorem, which is an equation that relates the two of them. The diagnostic power of a screening test is also given by positive predictive value. This is very, very important. So remember, the most useful test for a screening test is obviously the sensitivity. That's the most useful value. But the diagnostic power is given by positive predictive value. The probability that a person with a negative test actually doesn't have the disease, so this is very simple. This is going to be the negative predictive value. Right? So NPV, if the test comes out negative, how sure are we that the person actually doesn't have the disease is NPV. So these are the useful questions that come from the screening and the different one-liners and the formula that we have discussed. Now you have a few extra things from screening where you get questions. This is predominantly for INI-CT that you want to focus upon. Now, what they ask you is they give you this graph. This is a repeat Ames question, and they tell you that if B was my initial point where I was keeping my cutoff, if I change my cutoff from B to A, what will happen to sensitivity, specificity, NPV, PPV? So, what you want to remember is that this is our midpoint where I have tried to adjust between the true negatives, true positives, false negative, false positive. Do not overcomplicate this. Just remember what I'm telling you. When you go from B to A, can you see how false negative is reducing? Yeah, we are going from this number of false negative to very low number of false negative. That is how this curve is shifting. So when the false negative reduces, what should happen to sensitivity? You know that Fn is inversely proportional to Sn. So when false negative reduces, sensitivity increases. And again, n goes together, so negative predictive value increases, and obviously the other two p value values, SP and PPV, reduces. So this is what you want to remember from B to A. All right, this is what is the question that usually comes. What will happen to the values? The other type of question that you get is what about screening tests applied in series? Parallel. First of all, what is the meaning of this? And only then you will be able to answer it once you know the meaning here. So again, very conceptual. So let's say I am applying two screening tests, and if one is positive, only then I will apply the next screening test. So what do you think happens to the sensitivity? Overall, it falls, isn't it? Because we are dependent on this one screening. Only if it gives you positive result, I'm going to apply this, and only when that comes out to be positive, I'm going to say that you are screening positive. So obviously, sensitivity falls. But then when you turn out to be positive from both of them, means that you are definitely more likely to be positive. So that specificity increases. So this is more like mixed to give you a relatable exam. You have to appear for two exams. Only when you qualify both of them, you are certified to be a good resident. So your specificity increases, but the total number of people overall passing are going to reduce because you got to pass this and then you got to pass this. So overall, it keeps decreasing. So I think now it makes more sense. And n values always stick together, like we have seen. So when sensitivity falls, NPV falls, but PPV increases. That's how you remember this. On the other hand, parallel is when you apply two tests simultaneously, any of them are positive, you are basically going to increase. So here the sensitivity definitely increases, NPV increases, but specificity and PPV. Okay, so this is how we simplify this very difficult table otherwise. Now, again, very, very confusing is prospective versus prescriptive screening. What are these points? So prospective, oh, this is for the benefit of others when you're getting screened for others. Like in a blood bank, when I screen for infections, for hepatitis, for HIV, we are trying to prevent the spread of infection to others. That's why we are screening. Prescriptive screening is when you are screening for cells. For example, if I do a neonatal screening, prevent the spread of infection to others. Like in a blood bank, when I screen for infections, for hepatitis, for HIV, we are trying to prevent the spread of infection to others. That's why we are screening. Prescriptive screening is when you are screening for cells. For example, if I do a neonatal screening for hypothyroidism, all right, this is what I'm screening for that person, for that baby, whether they develop hypothyroid or not. So that is cells. This is about prospective and prescriptive why we are screening. Prescriptive screening is when you are screening for cells. For example, if I do a neonatal screening for hypothyroidism, all right, this is what I'm screening for that person, for that baby, whether they develop hypothyroid or not. So that is cells. This is about prospective and prescriptive screening. What is opportunistic screening? Again, a patient comes to you for some other disease, but you simultaneously screen for another association. Like a diabetic patient comes to the general physician, you simultaneously send that patient for a fundus screening to see whether the patient has developed diabetic retinopathy or not. So that is what is called as an opportunistic screening. All right. So this is what is the example that you can remember: diabetic patient getting referred for a retinopathy screening. No, so this is opportunistic screening. A multivariate screening, you can remember a general health checkup. When you go for a general health checkup, at the same time we are taking multiple samples. So you are drawing blood, then simultaneously you check it for sugar, also you check it for lipid, also you check LFT, RFT also. So overall, multiple things are getting tested at the same time. That is multivariate. So four types of screening, that are very confusing. So this is about screening in general. Now let's talk about tested. So quick screening, you can remember. Right, so this is what is the example that you can remember: diabetic patient getting referred for a retinopathy screening. So this is opportunistic screening. A multivariate screening, you can remember a general health checkup. When you go for a general health checkup, at the same time we are taking multiple samples. So you are drawing blood, then simultaneously you check it for sugar, also you check it for lipid, also you check LFT, RFT also. So overall, multiple things are getting tested at the same time. That is multivariate. So four types of screening, that are very confusing. So this is about screening in general. Now let's talk about incidence and prevalence. Believe me, you get so many questions, and this is the simplest thing ever, so don't get this wrong. So incidence is how many number of new cases you are detecting upon the total population at risk per unit amount of time. So first thing, incidence is a rate. You already remember which study we get incidence from. We get it from a cohort study because we need to see patients over time in order to detect new cases. So incidence is the number of new cases over the total population at risk into 1,000 per unit time. Okay, so this is incidence. Prevalence is a snapshot at one point of time how many number of cases are there. So this is a proportion. P for prevalence, P for proportion. This is what you get in a cross sectional or a snapshot study, isn't it? So this is the total number of cases upon the total population into 100. It's a proportion. What is the relation between them? Very important is PID. You know PID? So prevalence is incidence into the duration. This is how it gets affected. So you remember PID in this table becomes very, very easy. So what they ask you is all of these factors, how will incidence change? How will prevalence change? So whenever there is higher survival, what's going to happen? The duration increases, isn't it? So if there is increased survival, does the incidence change? No, new cases don't change. But what happens to prevalence? Equal height ID, so duration is increasing, so prevalence overall increases. We feel that there are more people, but no, it's just more survival which appears as if there are more diseased people. All right, so that's the concept. When you have increased mortality, what happens is the opposite. The duration reduces. So again, incidence is unchanged here, but the prevalence reduces. Faster recovery, same concept. Disease reduces, but again, new cases are not changing, prevalence reduces. What if you give extensive vaccination? In this case, now the number of new cases are reducing. What happens to prevalence? If incidence reduces, prevalence reduces. P equals I and D. Primordial prevention, if you apply, you don't let the risk factors come in. Obviously, incidence will reduce. And when incidence reduces, prevalence definitely reduces. So you get all of these as questions and they ask you what will happen to incidence, what will happen to prevalence. Okay? Now let's talk about biostatistics. One of my most favorite areas, biostats. We start from the basics and we build our way up from there. So when we talk about the different types of data, you want to remember the mnemonic.
No, Noel. यहाँ पे काफी कंफ्यूजन हुआ था.
Mnemonic, NOIR, NOIR. So we have four types of data: nominal, ordinal, interval, ratio. Many divisions of data can be done like qualitative, quantitative. I'm sure you understand that. Discrete versus continuous. When there are specific numbers, that is discrete. When you have something like blood pressure, which can be, in a continuous stage, that's continuous data. And the one which is most frequently asked is NOIR type of data. So let's understand how we define these. So when I say my data is male or female, black or white, depending on the continuous, when there are specific interval ratio. The basics and the build are made. What will happen to incidents, what will happen to evidence. Okay. Now let's talk about biostatistics. One of my most favorite areas, biostats. We start from the basics and we build our way up from there. So when we talk about the different types of data, you want to remember the mnemonic NOIR. NOIR. So we have four types of data: nominal, ordinal, interval, ratio. Many divisions of data can be there, like qualitative, quantitative. I'm sure you understand that. Discrete versus continuous. When there are specific numbers, that is discrete. When you have something like blood pressure, which can be, in a continuous stage, that's continuous data. And the one which is most frequently asked is NOIR type of data. So let's understand how we define these. So when I say my data is male or female, black or white, depending on the race, urban, suburban, rural, ABO blood group. So these are all qualitative data which have no real order in between them, or there is no interval in between them. So this type of data is what we call as a nominal data. Then when you have a specific order like TNS station, T1, T2, T3, T4, it's in one order. Yeah, so there is an order, but there is no meaningful interval between them. Likert scale. What is Likert scale? You must have seen, how satisfied were you with this service after any urban company or any review. They'll ask you for a review out of 5. How much would you rate our services? So that is Likert. It has an order. Same with Guttman scale and visual analog scale. Visual analog scale you must have seen in anesthesia. Will show you these 5 phases from this, to this, to this. How much is your pain? So the patient will choose that right now and in this state. So again, there's an order, but there's no meaningful interval. So this data is ordinal data. Order is there. So NO is what qualitative data. Now you have quantitative data like temperature scale. So when you have degree Celsius or degree Fahrenheit, it is arranged in order, meaning 35 degrees is more than 30 degrees. And there is a meaningful interval between them, but there is no true zero here. There is no true zero in degree Celsius or degree Fahrenheit, meaning 40 degrees Celsius is not the double of 20 degrees Celsius because there is no true zero. So this data is called as interval data, whereas ratio data is where there is a true zero which is there. So there is definite order and there is meaningful interval and there is a true zero like weight, blood pressure, pulse rate, sugar, hemoglobin, BMI, all of the other values which we have starts from zero and then there is a specific order. So this is how you have examples and they will ask you what kind of data is this and find out. Okay, so I've given you all of the examples and the concepts here. Now we go to measures of central tendency. Very, very important. But before that, we want to understand this curve, which is your Gaussian curve or your bell curve of normal distribution. Anytime you have any set of data which is distributed uniformly, it will have this bell shape. In the center, you have mean, median, mode. So The marker of a normal deviation is the fact that all of them coincide, all of them are equal and they are equal to zero. Meaning you have negative readings, you have positive readings, which are all spread out equally. Okay, so this is your curve of normal distribution. It is a Gaussian or a bell curve. Mean, median, mode are in the center, they are all equal to zero. Then what you have to understand? Standard deviation. Plus minus one standard deviation is the gonna include 68% of the population. Plus minus 2 standard deviation will include 95% population, and plus minus 3 standard deviation includes 99.7. Very important. 68, 95, 99.7% is the population included. What standard deviation will include 100% population? Infinity. Alright, so then 100% cannot be included in a normal distribution. So this is what you want to remember. Now coming to skewed data. In skewed data, they will give you these curves and they'll ask you whether there is positive skewing or there is negative skewing. So for this, you look at the tail. If the tail here is on the right side, like you can see, this is what is PR. You remember PR per rectals. You remember that when the tail is on the right side, this is positively skewed data. But when the tail here is on the left side, this is a negatively skewed data. Now, how does the mean, median, and mode relate here? For that, we have to understand that there are three measures of central tendency: mean, median, and mode. What do they mean? Mean means that you have a sum of all of the observations and you divide it by the number of observations. I'm sure you know average, you know mean. What is median is when I arrange all the data in order, the one which corresponds to the middle is the median. What is the mode is I just count which number comes in maximum number of times is the mode. So I'm sure you know these values. In a skewed data, how do they fall? So what we want to remember is that the maximum number of reading never changes, isn't it? So this at the top is always going to be mode. All right. So they can give you these three things and they can ask you which reading does it represent. So at the top is always mode. What falls in the middle? All right. The 50th percentile, as you can call it, is the median. So in the middle, we will always have the median, and the one value which always gets affected the most in a skewed data is mean, isn't it? So mean is always going to follow the tail. So this is mean. So this is how you can label these. All right, this is the simple conceptual way of labeling these. So now the one-liners on all of these. All right. So which is the best measure of central tendency overall? So this is mean. All right. So mean overall is the best measure. When they ask you for nominal data, so for numbered data, obviously the best measure is going to be mode. All right. So we can see which reading is coming the most number of times. For ordinal data, when you can arrange, we will take the middle reading, isn't it? So that is median. And for metric, overall, it is mean, isn't it? I hope this makes sense. Which is the measure most affected in skewed data? This is mean, as we have already discussed. Because let's say you are taking an average of 1, 2, 3, 7, 8. Suddenly, one skewed reading of 125 comes in. Your mean is what is going to be affected the most, isn't it? Your median will not be affected much. It will maybe go from one to the next one, but it won't be affected. Mode will be unchanged. It doesn't matter, the maximum reading will not be changed even if you add 2,000 to that number range. So least affected in skewed data is going to be mode, whereas if you ask you which is the most useful measure for skewed data, it becomes median, because mode is not something which is useful as a central tendency. It's just what is telling you that this is the reading which is coming the most number of times. So this is where you have to be very careful in these one-liners. Most effective, least affected, and most useful. All three different answers. And what represents the 50th percentile? If I arrange all of the readings into 100, what falls in the middle is the median, isn't it? So this is what takes care of all things about central tendency. Now,